The well-known Helmholtz decomposition is inspiring for us to construct two limiting cases. The first limiting case corresponds to the irrotational flow, and the second one demonstrates incompressible flow. As you see, if we select A to be a zero vector, so this term vanishes, and show F as another scalar quantity, which is commonly used in different literature, F is phi. So you can define U, the velocity field, to be the gradient of phi function. And take curl of the both sides. The curl of U is equal to the curl of the gradient of anything is 0. So the curl of gradient of phi, which is 0, is equal to the curl of U. So the curl of U is 0. This means that the velocity field, which is described by this condition, is curl-free or irrotational. So we call this limiting case the potential flow. And the scalar potential F, which is phi here, is the scalar potential, which we call it the potential function. The expansion of this relation, U, suppose that the velocity vector has components U, V, and W, and the gradient of phi consists of three partial derivatives of phi with respect to three coordinates in space, in Cartesian coordinates, of course. So far, we have supposed that the velocity field is only rotational. So the only assumption behind the definition of the potential function is the irrotationality of the flow field. Here, add another assumption and suppose that the velocity field is also incompressible. So the velocity field is divergenceless, also linoidal. And the divergence of velocity is equal to divergence of the gradient of phi. Divergence of gradient is the Laplacian operator. So the Laplacian of f is equal to 0. This is the well-known Laplace equation. So if you want to compute the phi function, the potential function, from the solution of the Laplace equation, the flow should be rotational and also incompressible. But the definition of psi only needs the irrotationality. Well, also you can validate the Laplace equation using this result from the previous section. You see, since the flow is incompressible, so the velocity field is divergenceless, so the Laplacian of f is equal to 0. Here we suppose that if f is equal to phi, so the Laplacian of phi is equal to 0. The second limiting case is the incompressible flow category, which you can see that, in contrary to the first case, we ignore the scalar potential f and suppose that the vector potential is equal to a new vector quantity, which is the stream function vector shown by psi vector. Again, if we define the velocity vector as the curl of a vector field, which is psi, and take the divergence of both sides, the divergence of velocity fields equal to the divergence of curl of the psi vector. The divergence of curl of any arbitrary vector is 0. So you see here we have a divergence of velocity field is equal to 0, which is the conservation of mass for the incompressible unsteady flow. This is the definition of the three-dimensional stream function vector. Based on the Helmholtz decomposition, you see in the first limiting case, u is equal to the gradient of phi, and in the second case, u is equal to the curl of the psi vector. Usually we use the two-dimensional version of the stream function vector because the use of three-dimensional version is somehow difficult and maybe it's complex. So the two-dimensional version of the psi vector, as you can see here, psi is equal to this a vector in three-dimensional space. Two first components are 0, and the third component is equal to the scalar string function. This is the vector string function. This is the scalar string function. Maybe you know this in different applications in fluid mechanics. And perform the curl operation here. You can easily compute the determinants to compute the cross product. And you will easily find that the u velocity, or the x component of the velocity, is equal to the partial derivative of the scalar psi function with respect to y. And the other velocity component is equal to the partial derivative of psi with respect to x. This is the y component. The partial derivative is with respect to x. This is the x component of the velocity. The partial derivative is performed upon y. We need a minus sign here because in the curl operator, we compute the determinant of submatrices, so a minus sign appears here. So the main assumption behind the definition of the stream vector or the stream function is the incompressibility of the flow field. In two-dimensional space or in three-dimensional space, no difference. But let's add another assumption here and suppose that the flow field is also irrotational. So the curl of the velocity field is 0. Again, perform the cross product operation and compute this determinant. The first row is the unit base vector, the second row is the del operator, and the third row is the velocity vector. So compute the determinants and subdeterminants, and you can easily find that the Laplacian of this scalar psi function is also 0. So again, if you want to compute the magnitude of the stream function using the Laplace equation, the flow field needs to be incompressible and irrotational. But the original definition of the stream function only needs the flow to be incompressible. Again, you can validate this relation from the equation obtained in the previous section. So since we have the irrotational flow, so the curl of the velocity field is 0. So the Laplacian of the A vector is 0. In the second case, we suppose A to be psi. So the Laplacian of the psi vector is also 0. In two-dimensional case, the Laplacian of the scalar psi function is also 0. The definitions are similar but different. You see the partial derivatives of the x component is over x, the y component is over y, and the w component is over z or z. But here you see we have cross derivation. The x component is equal to partial derivative with respect to y, and the y component with respect to x. Also, we have an extra minus sign here, but all terms are positive in the definition of the potential flow.